Okay, here's another example that we're going to apply conjugate beam to. Let's talk about the problem for just a second. It's a simple supported beam. You'll notice the load, 5 kips, is set off to one side, and it wants to determine the slope and displacement at the midpoint, which will be right here in the middle. So, what's the first step? We need to find the moment diagram. So let's do that. So before we proceed with the moment diagram, we need to find our reaction. So I'll just go ahead and pencil in here that I have AY and BY, and let's solve for those. So I'm going to first sum moments about A using right-hand rule and setting them equal to 0. So summing moments about A, my applied force will create a negative moment. That'll be 5 kips times the moment arm of 9 feet. And then BY will create positive moment about A, and that'll have a moment arm of 12 feet. So what's BY? I don't know, whatever that is. 45 divided by 12? What's that? 3.75. So 3.75 kips. And then I'll sum forces in the y direction. I'll assume up is positive. So I've got AY plus BY minus 5 kips. And since I know what BY is, then I can find AY, and it looks like it's 1.25. So there's my reactions. So now with those, I'll come over here and sketch kind of a template for my shear moment diagram. Assume positive X, positive shear with units of kips. So starting on the right-hand side, the left-hand side, what is the shear at A? Well, we have it going up of 1.25. And go over here at B. What's the shear at B? Well, it's 3.75, but notice that it's up, and that's negative shear on the right-hand side. So this should be negative 3.75. So don't forget that we know that the change in shear is the area under the load diagram, and that the slope of the shear diagram is equal to the load. So with those two things, we can figure out that first of all, there's no change in the shear. It stays that, and of course the slope is 0 because there's no load. We hit the 5, it goes from 1.25, drops down 5 to negative 3.75, and then again no change. So your shear diagram looks like that. So now let's see what the moment diagram looks like. The units here will be kip, feet. So what's the moment at A? 0. What's the moment at B? 0. So we just have to make those 2 points match. Now don't forget our relationships, that the change in moment is the area under the shear diagram, and that the slope of the moment curve is equal to the shear. So let's start first. So the change in moment over these first 9 feet should be the area under the shear diagram, which is 1.25 times 9. What was that, 11.25? And that's positive, so we go up to 11.25. What's the slope? or the shape of this curve? Well, the shape is equal to the shear, and the shear is constant and positive, so we have a constant positive slope. Now over the last 3 feet, the change in moment is equal to the area in the shear diagram, and that is negative 375 kips times 3 feet, which I think is negative 11.25, which is great. That brings us back to 0. The shape of the curve is the value of the shear. The shear is constant and negative. So you can see our moment diagram is shifted to the right just a little bit. Now we have to apply that as load to the conjugate beam. Let's see what that's going to look like. I'm trying to decide how I want to work this problem. I think I'll just do it down here. So here's our conjugate beam. So let's see how it maps. So an external pin in the conjugate system is a pin. And this external roller at B is still a roller. So our beam is going to look, from a geometric point of view, the same. What will change is the load. Now this is all positive load of a moment, so when we apply it as load in the conjugate system, it's going to be a positive load, and a positive load is up. So our load will look something like this. And that value there will be 11.25 kip feet, that's the moment, divided by EI. Everybody see that? Okay, we're kind of halfway, maybe a little more than halfway there. 60% through the problem.
So we're always going to use the same picture from the moment for the conjugate beam?
Right, because by definition the moment is the loading in the conjugate system. That's we got to find the moment first. Now this particular problem is asking for what? The slope and displacement at the midpoint. So that will be the shear and moment in the conjugate beam at the midpoint. There's the midpoint, which is about 6 feet. So I need to find the shear and moment there. Now, which side of this do you want to work? The left side or the right side? There shouldn't be a lot of choice. I mean, you can work both and they'll both give you the same answer, but I think you can see that the left side is just a simple triangular shape, whereas the right side is a triangle and a trapezoid. So just more to keep track with. So I think we'll work the left side. So if I need the left side, then what I probably want is the reaction at A. And I really don't care too much right now about the reaction at B. Okay? Now here's where it gets a little more tedious, and then we have to start working on this, is to find my reaction at A, I need to find concentrated forces that are equivalent to these distributed loads. And you can see that I have one load, which I'll call F1 for this triangular shape, and I have a second one I'll call F2 for that one. Now I'm going to sum moments about B to find my reaction at A, so I probably need these distances, which I'll call D2 and D1. You see that? So we're going to have to stop for a second and do some calculations and figure out what all that stuff is. They're acting through the centroids of the triangles. So I've got, let's see if I can maybe show you. So this triangle is F2, and the other one would be F1. So let's make those calculations. So I'll try to do it here. It's going to be organized kind of funny. Let's see, what should I do? Yeah, this problem's going to end up on a couple pages. All right, so let's start here. So let's start with F1. So what's F1 going to be? It's going to be 1/2 base, which is 9 feet, times the height, which is 11.25 kip feet, divided by EI. So what's that going to be? Somebody calculate that for me. And then F2 is going to be 1/2 base, which is 3 feet, times the height, which is 11.25 kip feet over EI. So what is F1? Anybody get that? 50.625? 50.625, and that's kip feet squared over EI. And this one's going to be a third of that. 16.875 kip feet squared over EI. D1 is going to be, first it's going to be a third of this distance, which is 9, so that's 3, plus 3 more will be 6. And D2 is going to be 2/3 of this distance. 2/3 of 3 is 2. Everybody see that? No? Why not?
I didn't see what you did. I was too busy.
Well, we want to find the centroid of this rectangle referenced from B. So anytime we measure from the small end of the triangle, we know the centroid is 2/3 the distance. And 2/3 of 3 is 2. Now this one's a little trickier because from the tall side, we know that the centroid is 1/3 the distance. So the base is 9, 1/3 of that is 3, but we have to reference it back to B, so that's plus 3 more. So it becomes 6. Okay? That pesky geometry, right? So let's now solve the problem. So now we're maybe 75% through. The problem is, what is the shear and moment at the centroid? Well, before we need to do that, we've got to find AY. So now that we have all these forces, we can find AY. Let's try that. So to find AY, I'm going to sum the moments at B. So as sum moments at B using right-hand rule, both F1 and F2 create what? Negative moment, right? So we'll start with F1. So I'll have negative F1, which is 50.625 kip feet squared over EI, times its distance D1, which is 6 feet, minus F2, which is 16.875 kip feet squared over EI, times its distance D2, which is 2 feet. And then I got AY times its distance, which is 12 feet. So when I solve for AY, I should get a negative value. You guys are going to have to help me with that. Anybody take a shot at that? This is roughly about 300, 330. Looks like it's going to be about 30 something. I'm just guessing.
32.5.
Anybody else get that? 22.5? That doesn't seem right. 28.1. 28 sounds better. 28.125. So I get 28.125, and that's going to be kip feet squared over EI. And negative. What's that?
No.
Wow. So let's keep rolling. So what comes next? Well, now I come back and I actually make a cut at the midpoint. So here's my beam. I cut at the midpoint, which is 6. I have my reaction at A, which is negative 28.125 kip feet squared divided by EI. And then I have a portion of the load. All right? And what is that value? Well, I know that the maximum height here is 11.25, but that's at 9 feet. So at 6 feet over, what would it be? It would be 2/3, right? 6 to 9. So what's 2/3 of 11.25?
7.5.
So this would be 7.5 kip feet divided by EI. And I would still be now looking, well, I would look now for the shear at this midpoint and the displacement at the midpoint. So finally, after all this work, we have a fairly simple problem to solve. So to do that, I'll get my concentrated force equivalent. I'll call it F3, and then of course it'll be at some distance. Now we know the triangle from the large end, the high end, that's 1/3 the distance. So 1/3 of 6 is 2. And we know that the force will be 1/2 base times height, so we can do that. So let's go ahead and finish. So finally, we're ready to go. So we'll sum the moments at the cut. Make sure they're in equilibrium. So let's start first with the moment that we're looking for. That's positive, the moment at the midpoint. F3 is going to create negative moment, and it'll be 1/2 the base, 6 times the height, 7.5 kip feet divided by EI. So that gets me the force, and then times the moment arm, 2. So again, force and distance. It's kind of hard to talk when you have one of these markers in your mouth. You notice that? Okay, then we have the reaction on the far side at A, and that's going to create positive moment. So that'll be plus 28.125 kip feet squared divided by EI times its moment arm, which is 6. So we should be able to solve for the moment at the midpoint. I'm guessing it's going to be negative, but you guys can tell me that. Well, this is 45, right? Negative 45, and this is almost 180. Should be like 120. So it should be negative 1. What is it? 123. So 123.75, and this will be kip feet cubed. Now the negative means that when we map this back to displacement, that means we have negative displacement. Negative displacement is down. Does it make sense that at the midpoint you would displace down? I say yes. That seems reasonable. Now, since we're already here, we can go ahead and actually calculate the value. So let's put some numbers in. We know that that's going to map to the displacement at the midpoint. So I've got negative 123.75 kip feet cubed divided by E. E is 30,000 kips per inch squared. I is 800 inches to the fourth. And then we need to convert between cubic feet and cubic inches, so we know there's 1728, 12 cubed, inches in a foot cubed. So that gives us a value of, looks like it's going to be really, really small. Yeah, I feel like we've done something wrong. What's the number again? 8, 9. Okay, that's close enough. Well, maybe it's not so bad. It's only a 5 kip load over a 12-foot beam, and the moment of inertia is 800. That's a pretty stout section, so maybe this is okay. That moment term seems small to me, but looking at the values, it looks reasonable. It just caught me off guard.
Why is the F3, why is that negative and not positive?
It's creating negative moment about the cut. Because I'm assuming right-hand rule, which is counterclockwise, and F3 is going clockwise about the cut. So let's go ahead and finish up and find the slope. So if I sum forces in the y direction, so I'll have my shear acting down, the shear at the midpoint. I have force 3 acting up. Unfortunately, I didn't calculate force 3, so I have to do it again. So I've got 1/2 base times height, 7.5 kip feet over EI. So there's force 3. And then my 28.125 kip feet squared over EI force acting down. So when I solve for the shear at the midpoint, it looks like I'm going to get a positive value. No, a negative value. What is that number?
Negative 5.65.
That's pretty small. Anybody else get that? 5.625? Yep. Okay, so 5.625, and this will be kip feet squared over EI. Now we know that shear maps to slope. So let's calculate that. So I've got 5.625 kip feet squared. And now I need to divide that by E, which is 30,000 kips per inch squared. I, which is 800 inches to the fourth. And now I need to get rid of this foot squared. So I know there's 12 squared, or 144 square inches in a square foot. So this should give me a dimensionless value, and it should be negative. And it's going to be really, really small. I think 0 point and probably a bunch of zeros.
3.375 times 10 to the negative 5.
Oh, I wasn't ready for that. Can you give it to me in decimal form? 0.00 what? How many zeros?
4 zeros.
1, 2, 3, 4, and then
3, 4.
3, 4. That's pretty small. It is negative.
Yes.
So what's happening, let's roll back and look at the top of the problem for just a second. What's happening here is at the midpoint is we're deflecting down, but the beam is still slightly heading down. It hasn't reached the maximum yet. So that means the maximum displacement, where you go from negative slope to zero slope, is still to the right of the midpoint, which makes sense because here we are at the midpoint, the load is to the right, so the displacement, maximum displacement, is shifted that way too. So I think conceptually this sounds like a good good values. Numerically, we may have lost something along the way, but I think it's reasonable. So, any other questions before I end this one? Probably your thing you're asking yourself, is this testable? And the answer is yes.